Okay, so there are several uniqueness theorems. So what we have seen before is the potential satisfies what? Del squared V equals minus rho over epsilon naught. This is the, Is that the sound?
Yeah.
So that's called the Poisson equation. In the region where it's vacuum, the Laplacian is 0, and that's the Laplace equation. Okay? So what we're going to do is talk about uniqueness theorem. Is that how you spell uniqueness? There are multiple. Suppose del squared V equal to 0. This is the vacuum case in a certain region. And I'm just going to and V is prescribed on the boundary of the region then the solution is unique. Then the solution for, or the expression for V is unique. I'm just stating the theorem as I know what it means. Please consult the textbook for an exact statement of a mathematical statement. So what is being said here is you have a certain region. Inside that region, potential satisfies the Laplace equation. Yeah, it satisfies this. And then in the boundary of the region, that means over here, the entire boundary of region, over here V is given to you. Yeah? If that's the case, there's only one V that satisfies Laplace equation. That is what the theorem means. Now, how would one prove this? It is easy because we've done all the hard work. Suppose not. Then there are at least two solutions. Two solutions, say V1 and V2. That satisfies the requirements of the theorem. Yeah? Correct? If it's not unique, well, there's at least two. Let V3 equal to V1 minus V2. then del squared V3 is what? Del squared V1 minus del squared V2, but each of which is 0. The entire region. Yeah? But on the boundary, in addition, V3 equals 0 on the boundary. What happens to Laplace's equation? What's special about the boundary? Very good. The maxima and minima occurs on the boundary. But look at this. V3 is exactly equal to 0 on the boundary. So what's the maxima of V3? 0. What's the minima of V3? So what is V3 in the entire region? 0. Therefore, V3 equal to 0 on the entire region. Well, if V3 equals 0, that's a good question. V is prescribed on the boundary. That means V1, see V1 and V2 satisfies the condition of the boundary. So that means V1 is prescribed, it's given to you on the boundary. V2 is also given to you, and it's the same thing. On the boundary they agree. Therefore, V3 is 0 on the boundary. Because they agree on the boundary. V1 and V2 may not agree in the inside, in the beginning, but the conditions of the theorem says that it has to agree on the boundary. So now, V3 is a solution to Laplace's equation such that it is 0 on the boundary. But maxima and minima occur on the boundary, so maxima and minima is 0. Well, therefore the function is 0 in the entire region, and if the function is 0 in the entire region, V1 equals V2. It doesn't tell you if the solution exists. So this is not an existence theorem, but what is it? Uniqueness theorem. Now this is, yeah, kind of clever, right? Kind of neat.
Yeah, and then the second line where we satisfied V3 with Laplace's equation, that also confirms that it's 0 in the region. Right? That's what, like, or what was the point of that?
Right. So, because only if V3 satisfies Laplace's equation, only then the maxima and minima is on the boundary. Otherwise, you could have a function just increasing from the left and decreasing on the right, or something, or a valley in between. Yeah. But there are no valleys or troughs to a Laplace's equation in the interior of the region. Just an amazing object. Okay, so I'm going to modify this to By prescribed, I mean somebody's given it to you. Now imagine V doesn't satisfy the Laplace equation, but it satisfies the Poisson equation. But you have been told where the charges are. There's no freedom in that. Remember, at the end of the day, this is electrostatics. Charges are not moving. Okay? Charges won't move till chapter 7. Yeah? Well, you might have a steady current in chapter 5. Steady current. Nothing changes in time. So up until the end of chapter 6, nothing changes in time. It's all steady. So in this case, in particular, it's electrostatic. So when I say del squared V equals rho over epsilon naught, we don't know what V is, but charge is given to you. It's that. So V must satisfy this equation. And on top of that, V is given to you on the boundary. And so, here is the proof. Proof is done. See, the charge density is given to you. So both V1 and V2 must satisfy Poisson equation for the same charge distribution. So V3 satisfies Laplace's equation, and that's all we really used. Yeah? Any questions? Travis? You've been, I know you've been unwell, but you've been watching the videos, right? Good. There is an even more neat uniqueness theorem, a third one. I don't want to write this sentence, it's a bit clumsy. You can, I mean, I could, but it's in the textbook. Let me actually describe it to you. So you have a region. And you know, this region can be at infinity too. Yeah? The argument applies. But now, this region is a conductor. What does that mean? Yeah, charges. Oh, no. Sorry. This is the conductor. So let me frame this figure. This is the hollowed out part. So this is a conductor. And moreover, there are several conductors inside. Huh? So, all right. You're gonna make me do this, right? So everything shaded in green is what? Yeah. Yeah? Everything shaded in green is conductor. So I suppose what is inside the amoeba? Oh, well, you know what I mean. What's it here? There's nothing here. Yeah? And then you're going to take charges. And you put a charge Q1. Just throw some charge in there. You take a pencil, a plastic pen, run it through your hair, then touch the material. Some amount of charge. You don't know how much. Oh, you do know how much, but you don't know how it's distributed. This is, let me call this say Q2, and Q2, and I don't mean to say there are only 3. There are many, so let me show that. Yeah, and this is QI. And this could be Q3. It would have been easier if I called it Q1. But the point is, we're not going to keep track. There's an outside boundary that's a conductor, and there are many, blobs of conductors in there.
Is this like some box?
It's a hollowed out box with conductors floating. Yeah? You can glue it on with like a wooden rod or something like that. Non-conducting rod. You learn so much from it. And then the claim is you have a unique electric field. The electric field in this entire space, so this is E. And the uniqueness theorem says uniquely given. Yeah? So what we're going to do is we're going to integrate something over a volume. What is the volume that I'm integrating over? The space in between, where there's no matter. Okay, we might call it vacuum, but it's not. In the language of physics, a field, like a potential field, is also something that is not vacuum. It's not vacuum, there's an electric field in it. Okay, so that's the volume we're going to integrate. And somehow we must show that E is uniquely given. So, suppose not. Then there are at least 2 solutions, E1 and E2, that satisfy the requirements of the theorem. So, let me ask you this. What is integral of E1 dot dA on the ith? So, I'm just going to do all the boundary integral. What are the boundaries? Because when you do a volume integral, and if you use divergence theorem, you're going to get a area integral. And the divergence, what area are we talking about? The area of the boundary of the volume. And what are the areas of the boundary? This one this one, and this one. So as I've shown in this diagram, there are 4 boundaries. But you could have many. It doesn't matter. But if I take the first solution and integrate it over the ith boundary. Remember Gauss's law? The integral of the electric field is what? It is, but it's also the net charge enclosed over epsilon naught. So I'm going to write, this is the ith surface. I'm going to get
You close that.
yep. Good. Now, remember, this is different from this. This is the first electric field. This is the ith boundary. And if they're both solutions, I'm taking the first solution and calculating it, the flux. But the net electric field, if they're both solutions, they describe the electric field everywhere. So if I take the first area, I better get Qi over epsilon naught. But this guy's also solution. One solution is not preferred over the other. So that also satisfies this condition at the boundary.
But then how are they,
I'm sorry?
are they the same? I mean,
Only at the boundary. No, not even at the boundary. Only the integral is the same. If 2 functions have the same integral, does it mean the function is the same? That's a trick question. It has to be true everywhere in the integrand, but this is totally different. In this case, it has to even be true here, away from the boundary. This one, it just says, when you integrate over this surface, for example, if I take E1 and integrate over this surface, I would get Q1 over epsilon naught. If I take E2 and integrate over this surface, I still get Q1 over epsilon naught, because they both satisfy Gauss's law, if it's a legitimate E. Fine. I did lots of area integrals for you. But to use divergence theorem, what do I need? I need a volume integral. So let E3 equals, what do you think it is? And I'm also let V3 be such that E3 equals negative gradient of V3. Yeah? But this is not end of proof. That's from the previous one. But these are conductors. So what's the additional information we have? They're equipotential surfaces. Therefore, V3 is a constant on all conductors. How do you know V3 is a constant on all conductors? Well, V3 is nothing more than V1 minus V2. Yeah, where V1, V2, they're all. So I suppose I should really say each of these guys have a potential. Since V3 equals V1 minus V2. V1 is a constant. V2 is a constant. Now the potentials I'm not saying are unique, but they're constant. And constant minus constant is a constant. And they're only constant on the conductor. I'm not saying it's constant everywhere, okay? So now I need a volume integral. So this is what I'm going to do. Integral over the volume of a trig. V3 divergence. The divergence. We're using the divergence theorem. Divergence. Now think about someone who thought this up. It's just hard work. There are two ways to write the divergence. On the one hand, this is gradient of V3 dot E3 plus V3 times divergence of E3 d tau. In the volume that we're integrating, what's the charge in this region that we're integrating? What's the charge? 0. So I'm just going to write this integral over here, just because of lack of space, and I need most of what we're talking about. Maybe I can even go here. The diagram is important too. I get the volume divergence of V3 E3 d tau. I want you to tell me what I did. Of course, this has gone to 0. And I'm going to write the answer and tell me how. It's a simple one. Where did I get that? Obviously from here. How did I get that? I'm sorry, not divergence.
Oh, the gradient. Yeah.
Gradient
Yeah.
is the negative of the electric field. Now, here's an interesting fact. This is just the magnitude of E3 squared, right? So I can write this as E3 squared d tau.
You rewrote the volume integral over the divergence.
So I started from here.
Okay.
Yeah. Ignored this term, replaced it with that. Now, this is the magnitude of a vector field squared. This is a positive quantity. If I integrate positive quantity over a certain volume, what will I get? Yeah, so this over here has to be greater than or equal to 0, because E3 squared is never negative. If you increase, if you integrate 2 over a volume, right? If you integrate x squared over a volume, you're going to get a positive function. Fine. Now we do the reverse. We have the divergence theorem. What is that? On the other hand. But on the other hand, right? all the boundary terms. I guess I should say all the boundary terms. Oh, E3. From here, what is E3 on the boundary? First of all, is this a constant? Potential is a constant. I mean, I said it, but for a reason. Why is it a constant? Is on a conductor. So I can let me do it this way. V3 E3 dot dA, first of all, is equal to V3 E3 dot dA, because it's a constant, equal to V3 E1 dot dA on the boundary minus E2 dot dA on the boundary equals V3 times QI over epsilon naught minus Qi over epsilon naught, which is what? Because these two guys agree on each of the boundary. That's equal to 0. You see, when ideas are bigger than a chalkboard, we have to keep recycling pieces. So we have shown that this is equal to this, but this is also equal to this, which is 0. Therefore, 0 equals how can you integrate a non-negative number and get 0? How can you integrate a positive function and get 0? Function has to be 0. This is greater than 0, but, well, it is 0, in fact. This has to be 0. Anytime this is greater than 0, it's going to give you a 0 value. Implies E3 as a vector, because if the magnitude of a vector is 0, surely the vector is 0. E3 equals 0 everywhere. What does that imply? Now you might say, all right, I see it. What? What am I going to do with it? Right? So you need a problem that anchors this argument. So we go back to our faithful Death Star. So the proof is over. And this is an example from chapter 2. In chapter 2, Griffiths has he has a prophecy. He says, I'm just going to assume this, I'll prove it in chapter 3. So instead of doing it that way, I just waited till we got to the uniqueness theorem, and then we're going to discuss the example. Let me actually mention the example. And now that I've mentioned the example, you should hear his argument. You should read his argument. It is, claim of a prophecy to be fulfilled later. And I hate prophecies. Example 2:10. Oh, that took right like a Hagorama jug. Felt different. Let me see if it does any. Oh, much better. In my mind, I wasn't prepared for a good jug. So, you take a sphere, a conductor, then you hollow out this conductor. So this is the hollow, this is the conductor. This is hollow, except for what? I'm going to take in this hollow and put a charge Q here. Yeah? The question is, what's the electric field outside? Let me give you the answer first, and then I'll go through the argument. The conductor shields everything. Now, why is that argument true? This is my volume. Yeah? Whatever I do to the electric field, E dot dA over here should be Q over epsilon naught. Because if I put a charge Q here, what's going to happen? Well, that's the only charge inside. But you can expect, see, the electric field here is 0, right? So this guy is going to attract minus charge over here. Where's that minus charge going to come from? Positive charge over here, because inside the conductor there's no net charge. So there'll be exactly minus Q over here, and this plus Q and minus Q will cancel this off, and there will be plus Q over there. But it has to be uniformly distributed. This is not uniform. But this satisfies E dot dA equals Q over epsilon naught. In this case, there is a solution, existence. From the theorem, it is the only solution.
So what if it's inside the conductor?
Inside the conductor? Oh, I got an answer for you there. Yeah? What about inside here? Oh, from that point. Isn't that neat? So while you're puzzled and you have this love-hate relationship, well, if you have this hate relationship with electrodynamics, I'm trying to argue that you should also have a love relationship with electrodynamics. Yeah? It's just amazing. Look at how, so go through this argument. It's not a difficult argument, but let it settle in. You should always revisit this argument. I have 2 minutes. I'll tell you a story.